Okay, well, welcome to our first tutorial, which is a innovative flops this year. We're delighted to have Neng-Fa to give us a tutorial on Picat. So we talked a lot about constraint programming, and one of the topics that came up this morning was, for example, CHR. And Neng-Fa was very quick to point out that there are much more efficient realizations of constraint solvers, and I'm sure in his tutorial he will point us to a particular system that gives us a very efficient form of constraint solving. So this is really a continuation of our thread on realizing ideas as systems. So please enlighten us on Picat. And thank you very much for volunteering to educate us about the proper way of solving constraints. That's superb.
All right, thank you, Andy, for your kind introduction. And well, I would like to thank the chairs for giving me the opportunity, and also thank you all for staying here for my talk, not going to the spa. And this presentation includes contributions by several of my colleagues worldwide: Picat in Sweden, Jonathan Fruman in New York, Roman Batak in Czech Republic, Agostino Dovia in Italy, and Sergei Dimchenko in Seattle. So basically, I will be answering two questions. What is Picat, and how to use Picat to solve problems? Well, actually, there is a big question. Why Picat? And actually, I want to avoid this question. Why? Because we could assemble a panel here and spend several hours discussing what the next generation of program languages should look like. Well, to make the answer short, we all pursue ever better program languages that are easy to write, easy to read, easy to maintain, or robust, and or efficient. There are many other criteria. Well, the direct reason is for this language was I had been working on Prolog implementation for many years. Really, my students didn't like Prolog, and they didn't show respect at all for the language, and at the end, they didn't show respect for me either. So I wanted to design a new program language they like. Yeah. Many people say logic programming concepts are great, but Prolog really sucks. So what I wanted to do is to design a language to make logic programming concepts more accessible to a large, broad audience. All right, what is Picat? Well, first, the name. It's an acronym. Each letter means something. P for pattern matching, I for intuition, intuitive programming, C for constraints, A for actors, T for tabling. So I will touch on, each of these features in my talk, except for actors. Actors work behind the scene, actually, constraint propagators or actors in Picat. So also the pronunciation, there is a standard pronunciation, which is Picat. Yeah. So many people pronounce it Picat. Actually, I used to pronounce it this way until I met some prominent people who said, I don't like this pronunciation. It reminds me of this PK. I don't like it. So we changed it to Picat. All right. So this language what is a multi-paradigm language which amalgamates many features from many languages. It shares with Prolog the core logic programming concepts, including logic variables, unification, and non-determinism implemented through backtracking. But this language delivers these features, logic program features, in a more accessible way. Okay. So for example, arrays and maps are also terms. Can you imagine a program language that don't have arrays or maps? And also, rules in this language are pattern matching rules. Okay, unlike unification-based clauses in Prolog. Okay. You can still use unification, but you have to use it explicitly. Okay. And it supports non-determinism implemented through backtracking. Okay, but it is explicit non-determinism. That means, okay, if you want to backtrack, a rule to backtrack, you have to denote it explicitly. Well, the design principle is similar to the design principle of Python. Okay, being explicit is good. Being implicit is bad. Yeah, that's the first motto of Python design. Yeah, and Picat also took a lot of features from other languages, including functional programming, Python scripting languages. It supports functions. Many computation tasks are deterministic, for which functions are more convenient to use than relations. Yeah. And Picat supports loops, yeah, for describing repeated computations. Yeah. Well, we know repetition can be written in either recursion, in both, yeah, recursion and iteration. Okay, many people say recursion is good, it's declarative. Iteration is bad because it's imperative. I don't see it this way. Yeah, well, sometimes you write a recursion, using recursion, it takes 10 pages to write. If you use loops, it takes 1 page to write. Then which one is more declarative? So in my opinion, being declarative means concise, yeah, and more readable, more writable. So Picat supports loops. It also supports list and array comprehensions for building lists and arrays. Okay, these are just special functions. And Picat also supports assignments. Okay, which is taken from imperative languages. But unlike imperative languages, where assignments can have rampage side effects. Okay, in Picat, side effects from assignments are limited in scopes in a manageable way. Okay, so I will talk about these features. Okay, later. And Picat provides facilities for solving combinatorial search problems, including tabling for dynamic programming problems, 3 solver modules, CP, SAT, and MIP for constraint satisfaction problems, and a planner module for planning problems. Okay, this is the outline of the tutorial. So it is made up of 4 parts. Okay, the first on the basics, nuts and bolts of the language. Second part on combinatorial search facilities. And the third part, it's a typo, yeah. I will present the highlights of papers. We and also third party authors have written about Picat. And the fourth part is a demo. All right, the basics of the language. Okay, so I will talk about data types and built-ins, statements, and how to write logic style programs, functional style programs, and scripts. Yeah. So, the first feature, the first logical program concept supported by Picat is logical variables. A logical variable is just like a variable in mathematics. Yeah, it is a value holder. Yeah, you can put values, okay, inside of the holder, and a value has a type. This language is dynamically typed language. That means types are checked at runtime. Okay, so everything, okay, is a term. Okay, a term can be a variable, can be an atomic value, and it can be a compound value. And a variable, okay, can also be an attributed variable and a domain variable. Okay, atomic value, okay, can be atoms, numbers, and so on. And a compound value can be a list or a structure. A list, a string is a special kind of a list, just like what you see in Haskell. Okay, and there are arrays and maps and sets. Okay, these are also compound data types. So I'm sorry, I know you are experts. You will get bored, but this is a tutorial, so I have to go through this very quickly. Okay. So variables, a variable name begins with a capital letter, just like variables in Prolog. Okay. So these you can use var to check if a variable is a variable. Yeah? Okay. This is something people from imperative languages don't understand. A variable is the address of a memory location. If it is a variable, then it is a variable forever. How can you check it? Yeah. But in logic language, it's different. It's a value holder. Okay. If it holds a value, then it is not a variable anymore. Yeah. Okay. If it is free, then it is a variable. Yeah. A variable can become an attributed variable. Okay. Once you attach an attribute to it. And you can use get attribute to get the value associated with the attribute. And you can create a domain variable. Since domain variable built-ins are provided by these constraint modules, you need to import one of the modules before you can use these built-ins. So we import cping, and we create a domain variable. Well, atoms are symbols. Yeah. Okay, atoms can be coded and it can be uncoded. Uncoded name begins with a capital letter, with a lowercase letter. Okay? And a character is just a single letter, atom. Well, you can use atom to check if a term is an atom. Okay, you can use check if char to check if a term is a character. You can use odd to get the code. Okay, in here it's a UTF-8 code, yeah, of a character, and you can also convert a code to a character. Numbers are not different from numbers you see in other languages. Okay, here you see by default numbers can be infinite precision as long as you can write, as long as the computer has enough memory. And also you can give numbers, binary numbers, octal numbers, hexadecimal numbers, lists. There are different ways you can write lists. Okay, you can write a list by listing the elements in the list. You can also use this new list to create a list by giving the number of elements you want to create. And when you use this new list, okay, you create a list. Okay, in the beginning, all the elements are, single are free variables. You can also use a range, okay, from 1 to 10, okay, with step 2. You can also write lists implicit by using a list comprehensions. Yeah, in this example, okay, it is a list of x. X is in the range from 1 to 10, and the property, yeah, the property is, okay, x is even. Well, there are actually a large number of built-ins on lists. For example, use len to get the length, and use plus to concatenate two lists. Okay, one thing you need to notice is linked lists. Lists are linked lists, so length, when you access the length, it takes linear time to get the length. Well, strings are just special lists. okay, a list. And well, this is how to say, actually we thought about it is when we designed this language, okay, at the end, okay, we just learned from Haskell, okay, so make strings, special lists of characters. Well, it may be a waste, yeah, to store a string as a list because it takes too much space, but it's very convenient, okay. Structures. Okay, you can create a structure explicitly by writing a structure with the name and a list of arguments. Okay, you need to denote a structure explicitly by preceding the structure with a $sign. Okay, just to tell the system it is a structure, not a function call. Yeah, this is special notation. I think I took this from early version of Haskell. Haskell doesn't have this anymore, right? Early version, yeah. I store it. I store a lot of things. So actually, Picat, another name is called Copycat. And you can create a structure by giving it a name and the number of arguments. So again, you can use you can create special structures. Okay, for special structures, you don't need to precede it. Okay, precede them by the $symbol because they can never be function calls. All right, arrays are like lists, but arrays provide constant time access. Okay, again, you can create arrays by listing the elements explicitly. You can create an array by using this new array function. Okay, you can create multiple dimension arrays. You can also create an array using an array comprehension. And all the built-ins on lists are overloaded on arrays, almost all, yeah? Okay, so, but there is one difference, is, okay, arrays provide constant time access. For example, you want to access the length of the array, you get the length immediately. You don't need to traverse the elements. You don't need to count. All right, maps and sets, or hash tables. Okay, you can use new map to create a map. Okay, you can initialize a map with a list of key value pairs, and you can use a get to retrieve the value associated with the key. And you can use get with three arguments, yeah, passing it to default value. So in case there is no value associated with the key, then the default value is returned. A set, okay, is also a hash table. Okay, so it is just a set of keys, no values. And you use has key to test if a value is in the key. You can use this index notation to reference arguments, okay, of a compounder value. So you need to pay attention, as I said before. Linked lists don't provide constant time access of elements. So you can use this index notation, but you have to be careful. This notation takes linear time, okay? And, well, however, for structures and arrays, okay, so you do have constant time access. List comprehension is a special function for creating lists. Well, this is a general syntax. Well, the semantics is also very simple, yeah? So this E in D, we call it an iterator, okay? So for each value, E1 in D1, En in Dn, if all the conditions are satisfied, then T belongs to the list. All right. So, well, many languages support the list comprehension. Okay, in here, okay, so you can write, also parallel loops. We call parallel loops. Yeah. So if you write this, A in A, B, and I in 1, 2, then you get all the combinations. Okay, you can use. Okay, AI is appear in the zipped list, then you get A1 and beta. But actually the compiler is pretty smart. It doesn't evaluate the zip function to create a zipped list and then iterate over the pigs. The compiler is smart, yeah, it avoids creating the list. Oh, and you need to pay attention to scopes of variables. Okay, so if a variable occurs in a list comprehension, okay, such as x in here, if it only occurs inside of the list comprehension. Then it is local. It is local to each iteration. Yeah. Okay. So you see, this one creates a list of different variables. If X occurs before, okay, in the outer scope, okay, as this X occurs before, right? Okay, then this is global, called global. Then all the iterations share the same variable, so you create a list of X's. Okay. And Picat also supports OP notation, okay, for chaining function calls. So, well, O dot something, F something. Okay, if O is an atom, then it is a module qualified call, and O must be a module name. Okay, otherwise it is just a different notation, okay, for this predicate or function call. Okay, as here you can use, it's pretty convenient actually. Okay, a lot of users like this. You can have, okay, many function calls, you can chain them. Yeah. Well, unification is an important operation supported by Picat. Okay, as I said before, you have to write unification explicitly. Yeah. So it is a powerful operation which subsumes many other, more specialized operations, such as binding, test if two terms are identical, or matching, one-way matching. Okay, and also occur checker is not done. So, so if you unify X with Fx, it succeeds. But if you want to print out the binding, then it never ends. Well, all this, okay, it is logic, how to say, supposed relations. It supports non-deterministic predicates for which, okay, there are multiple solutions. Well, for example, member X, okay, you say member X is a member of the list, 1, 2, 3. So what is X? Okay, then the system can return multiple answers. Okay, this is the same as in prolog, yeah. And you can use once operator to control backtracking. In case you just need one solution, then you can use this, okay, to prune the search space. And high order calls, you can use high order calls, call to call predicates, use apply to call high order functions, use map to map a function onto a list, and use find all, okay, to get all the answers that satisfy a call. And time is also a high order call, a time call, and you just make it a call, and then the system tells you how much time was spent on the call. Okay, you can use max of, min of to get a minimum value or maximum value, okay, of all the instances that succeeded. Also, there are global maps. Global maps are pre-created. Okay, they are provided for convenience. There are 3 types of global maps. Okay, heap map is created on the heap. Okay, and changes are undone upon backtracking. Okay, so that means, okay, in a search tree, you create a map. Okay, make changes, okay, on one path, but when you backtrack, okay, all the changes will be undone. So when you go on to a different path, okay, then you cannot access data created in a previous path. Global maps and table maps are different. Okay, they are global. Okay, so that means because changes are not undone upon backtracking. That means, okay, you go along a different path, you can still access data created in previous paths. Okay. Global maps are created in the global area, and the table maps are created in the table area. Okay, this is another feature. Table maps, all the keys and values are hash const. Okay, that means, okay, if you have a component, okay, if it is the same, then it is only tabled once. Okay, this is good for certain applications. Yeah, where you don't want to duplicate the data. There are modules. Okay, so I/O. Okay, maybe it is surprising to many of you. I/O is preloaded because I don't like so input I/O, input list, input array. So it's preloaded, and also math module is also preloaded. Okay, utility module is not preloaded. Okay, it provides several useful utility built-ins. Okay, for example, split. You can split a string into tokens and use join to join tokens into a string. Okay, you can find the permutations. Okay, one by one, or you find all the permutations. Okay, into a list. All right, so each predicate call is a goal. Yeah, is a primitive goal, and you can compose goals. Okay, by using connectives. This comma is a conjunction, and a semicolon is disjunction. Not is negation, and you can write if then else. You can also write prologue style if then else. All these are from prologue except for if then. Yeah, and you can use conditional expressions. Okay, if a condition is true, okay, then return one value, otherwise return another value. Exceptions. Okay, you can throw an exception during execution of a program. You can throw an exception. Okay, if the expression is captured by a catch call, then it will be handled. Otherwise, the system will handle it. All right. So loops. The for each loop is the best type of loops. All right. This is syntax. Again, you have iterators and conditions. Okay, the semantics is very simple. So for each combination of values, okay, this goal is executed. Here again, you need to pay attention to the scopes of variables. Okay, it's the same scoping rule is used. Variables that occur within a loop, but not before in its outer scope, are local to each iteration. So for example, here x is a local variable. So then so you have different variables. Okay, in this one, x occurs before the loop. Yeah, before the loop. Then it is global to all the iterations. Okay. Assignments. There are two types of assignments. Okay, the first type has this index notation on the left-hand side. Okay, this assignment updates the component, referenced by this index notation. And this update is done upon backtracking. Okay. The second type of assignment is the left-hand side, has a variable, has a variable. So for this type of assignment, the compiler introduces new variables. Okay, so for example, for this assignment, it introduces a new variable var prime, and then replaces all subsequent occurrences of var by this new variable. Okay, in this example, so we have an assignment x, assign x plus 1 to x. Then the system introduces a new variable x1, and for the second assignment, it introduces another new variable x2. So in this way, you don't need to reinvent variables. That's good. Yeah. So in this way, you can use the same variable to store values at different stages of computation. Yeah, it's provided as a convenience. Well, since we have assignments, then it makes sense to introduce while loops, right? So the semantics is not that much from while loops in C. Yeah. So for each condition, while the condition is true, you execute this goal. All right, I have talked about the basics, basic types, and basic built-ins and the statements. Okay, now we are ready to write programs. So first, how to write predicates. All right, predicates are written by using these two types of rules: non-backtrackable rule and backtrackable rule. These rules are pattern matching rules. Were actually Weda-san mentioned. Had a great talk about guarded home clauses. In some sense, it is similar to guarded home clauses, but there are big differences. The first big difference is you see